Hi students, Professor Nugent here. In the last video, we just showed that the sum from I equals 1 to n of xi minus x bar squared is equal to the sum from I equals 1 to n of xi times xi minus x bar in parentheses. And now I'm going to substitute this term into our expression for beta 1 hat, and that's going to make our exercise in proving that OLS is consistent a bit easier. All right. So what we had originally, let's write this down, beta 1 hat is equal to, we dropped that term connected to the intercept, the beta naught, because that was multiplied by 0. And then we're left with beta 1 times the sum from I equals 1 to n of xi 1i minus x1 bar times x1i all over the sum from I equals 1 to n x1i minus x1 bar squared plus sum from I equals 1 to n of x1i minus x1 bar times ui all over sum from I equals 1 to n of x1i minus x1 bar squared. And then we're going to substitute in, as we just showed, this is equal to the sum from I equals 1 to n of x1i minus x1 bar squared. So it's equal to beta 1 times the sum from I equals 1 to n of x1i minus x1 bar squared over sum from I equals 1 to n x1i minus x1 bar squared plus sum from I equals 1 to n x1i minus x1 bar ui all over sum from I equals 1 to n x1i minus x1 bar squared. Very good. That is equal to 1. That's equal to beta 1 plus sum from I equals 1 to n x1i minus x1 bar ui all over sum from I equals 1 to n x1i minus x1 bar squared. We can multiply and divide by n to the power of negative 1 so that we can use the law of large numbers to conclude that these sample statistics are going to converge in probability to their population quantities. So we can write that the probability limit of beta 1 hat is equal to beta 1 plus, now 1 over n times the sum from I equals 1 to n of x1i minus x1 bar times ui. I mean, you could write like ui minus u bar, or u bar is 0. This is the covariance of x and u, right? Covariance x, u. And we're writing this in terms of the population quantity. We're concluding that in probability, the sample statistic converges to the population quantity, and we are employing the law of large numbers to make that conclusion. Okay, and we have the same for the denominator. This converges to the variance of x1. But the covariance between x and u is 0, right? That equals 0, so this term goes to 0, and the probability limit, the plim of beta 1 hat, is equal to beta 1, which is what we wanted to show. Proof concluded. Fabulous. So we used the multiple linear regression assumptions 1 through 4. We do not need homoscedasticity. We do not need normal errors. We just need the population regression function to be linear in parameters. We need a no perfect collinearity we need the zero conditional mean assumption, and we need, I forget which ones that I did say and which ones I didn't, but we need the fourth one. And the variances must also be finite. All right, the variances must also be finite. We also must have that the variance of x is positive. But the variances must be finite. Okay. So let's add on to this. Let's add on to this a new assumption, which is a revision to the fourth assumption. The fourth assumption, the multiple linear regression assumption number 4, is the zero conditional mean assumption. And we're going to make a revision to that, the zero mean and zero correlation assumption, that is the expected value of u is equal to 0 and covariance of x and u is equal to 0. Now, the initial or original multiple linear regression function 4, that is MLR.4, that is the expected value of u given x1 through xk is equal to 0. This regression, this assumption implies this assumption. Okay, so the assumption up here that the expected value of u is equal to 0, the covariance is equal to 0, is a less strict assumption that is implied by the zero conditional mean assumption. The zero conditional mean assumption is more strict. Okay. So this one, the zero conditional mean assumption, this implies that any function of the explanatory variables must be uncorrelated with u, which is much more strict than what you have up here with the zero mean and zero correlation assumption. With that, we only require that each xj is uncorrelated with u in and of itself. Okay, so this is a bit weaker, and what we're going to show, what we can show is that, let me not get ahead of myself. So when we assume zero conditional mean and this thing, the reason that we like to assume this thing is if we make this assumption that we're going to get the population regression function correct. So we are assuming that we are getting, if we make this assumption, then together with our other assumptions, we're assuming that the linear model that we specified, that's the right model. So based on this assumption, there's nothing that there's no other nonlinear dependence between the error and the explanatory variables that we did not consider. So that's why we make this strong assumption, because if we make the strong assumption, then we're saying that the model that we are considering is the right one. So we just use this as useful for interpreting the OLS estimation of a linear model as providing the best linear approximation to the population regression function. But these are going to come in handy. Okay? So what I'd like to do now is conclude this video here, and then stay tuned to the next video when we will talk about and specify inconsistency. Thank you.